Hi, everyone. Welcome to Greg's 1-hour Compass seminar. Today we have Greg Koman. He got his undergraduate degree at University of Massachusetts Amherst. He got a BA in English and a minor in math and stats. He's currently in the NPO department, and he's at the end of his 5th year, and he works with Dr. Bill Johns. His favorite brewery in Miami is called Unseen Creatures, so reach out to him to get his beer recommendations from Unseen Creatures. And today he's going to be talking to us about circulation and overturning in the Eastern North Atlantic Subpolar Gyre. Over to you, Greg.
Great, thank you, Mary Beth. I'm just going to share my screen. Okay, so everybody can see this. I don't know nobody's video's on anymore, so I'm going to assume yes, and somebody will tell me if not. But yeah, thank you, Mary Beth. As she mentioned, I'll be talking about circulation and overturning in the Eastern North Atlantic Subpolar Gyre. And I have many people to thank for this presentation, including the National Science Foundation for their funding, my advisor, Bill Johns, my PhD committee, research group, some additional collaborators, and my wonderful wife, Dana. So the outline today, I'm going to start by talking about a relatively unknown flow called the East Reykjanes Ridge Current that if you've been to one of my seminars before, I've talked about previously at one point or another. Then I'll continue into new estimates of the North Atlantic Current into the Iceland Basin, part of the Eastern North Atlantic Subpolar Gyre. And then I'll finish up by kind of trying to do a mass budget and talking about the overturning budget and seeing how things have changed or are changing in that region. So to start, I'll mention that I'm part of the Overturning in the Subpolar North Atlantic Program, or OSNAP. And this group is a multinational collaboration of a number of different institutions worldwide in North America and Europe and China. And we together maintain the first continuous Eulerian observations across the entire northern North Atlantic, from Canada to Greenland, and then from Greenland all the way over to Scotland. And the section that we maintain, as in Miami, and Bill Johns' research group, is right here in the Iceland Basin, just to the east of the Mid-Atlantic Ridge, or as I'll refer to it as the Reykjanes Ridge, the section of the Mid-Atlantic Ridge that's the closest to Iceland. So this is what a lot of my presentation will be about today. Here's an overview schematic of the same region. The triangles represent all those moorings that I just showed, and to kind of orient where we are and where the East Reykjanes Ridge Current is. There's its location just to the south of Iceland on the eastern flank of the Reykjanes Ridge, moving to the southwest direction. And you'll see that I'll end up looking at those magenta colored triangles. Those are the moorings I'll end up using for this first part of the presentation. So to start with the East Reykjanes Ridge Current, to figure out how much transport is here, my quick kind of section here on data and methods. There's 2 moorings here on the western edge of the East Reykjanes Ridge Current at the top of the Reykjanes Ridge, and there's 2 flows going in opposite directions there. We have the southward flowing East Reykjanes Ridge Current to the east, and then on the western side of the ridge, we have the northward flowing Irminger Current. And so using data from a mooring that's maintained by a group in the Netherlands, IC4 is labeled there, and our first Miami mooring, M1, I find the 0 velocity line between the mooring at each time interval, and I integrate the flow to the east of that. Then below 1,200 meters at depth, where we have a bunch of current meters and TS recorders, I find the 27.8 isopycnal, because everything below 27.8 is considered kind of the classic Iceland-Scotland overflow water mass. That's the formation waters of, or part of the formation waters of the North Atlantic deep water. So above that is what I am considering East Reykjanes Ridge Current water, then I find that transport by gridding those current meters. And then finally, that rectangular section up top between moorings M1 and M2, I take the difference in dynamic heights to get the relative geostrophic flow there, and I reference it to 1,200 meter current meters. And so the combination of those three sections together add up to what I'm defining as the East Reykjanes Ridge Current. So for some results, 4-year analysis shows that the East Reykjanes Ridge Current is about 12 sphere drips in strength. As you can see there, it's highly variable with variations in timescales of days to weeks or even hours. I actually did an analysis as part of the paper I was writing on this that said that 1/7 of the time, the transport actually changed by more than 8 sphere drips within a 48-hour period. So it changes very rapidly in this location. It's extremely variable. And the flow is mostly barotropic. You know, I have labeled there quasi-barotropic, and you can see from that image that's the velocity profile, and the red star kind of indicates where our 1,200 meter current meters are located. But you know, there's a little bit of baroclinic shear there, as you can see, but for the most part, it's a very barotropic flow. If I break down the ERRC into some of its components, that baroclinic transport you see there contributes virtually nothing. In fact, it's 0.1 sphere drip in the opposite direction relative to what I'm referencing them to, the 1,200 meter current meters. But the barotropic dominates the flow here. It's just in that rectangular section I showed a moment ago, above 1,200 meters between those two tall moorings. It's 7.5 sphere drips. That section of it constitutes 7.5 sphere drips of the total ERRC. Below it, the gridded current meters finds another approximately 3 sphere drips of flow, and you can see in the third panel that it's a relatively steady flow there of doesn't get beyond 0 to maybe 7 or 8 sphere drips very often. And then to the west, that little section at the top of the ridge where I find the zero velocity line between the two countering flows has a little bit of seasonality, as you can see in this image, in the late winter and early spring. But it's worth noting that the ERRC as a whole doesn't have really any seasonality or statistically any seasonality. So those increases in transport in that season seems to be kind of like a meandering of the flow a little bit up to the upper ridge, as opposed to an actual full increase in transport. If we take a look at some Hofmahler plots, the Hofmahler plot on the left are the reference current meter velocities that I use to calculate my transport. And then, on the right, they're the ones that I use to calculate my transport. On the left are surface velocities from altimetry. And these two Hofmahler plots agree in the sense that they both identify the East Reykjanes Ridge Current as a pretty narrow flow to the upper ridge, about 80 kilometers wide between moorings M1 and D2, as I have labeled there. But how they disagree is not only in their consistency. You can see that in the current meters, it seems very steady, always there between M1 and D2. But the velocities are quite a bit different. The current meters have a mean velocity of about 11 centimeters at their maximum, 11 centimeters per second, whereas the altimetry-based velocities have a maximum of about 6 centimeters per second. And so this results in a difference of about 3 or to 3.5 sphere drips of transport, you know, just when I reference that one section for the overall flow in the region. So this brings up a little bit of a discrepancy between altimetry reference transports and current meter reference transports. So the next thing that we decided to look at was the Argo data in the region. And the Argo data not only can give us an idea of how much flow there is, how much transport there is, but it also gave us the ability to kind of piece together what's happening in the region. So on the right, you have 1,000 meter current, 1,000 meter drift data from Yamaha Argo drift. And then on the left is surface velocities inferred from those 1,000 meter Argo drift data, you know, and then using Argo data to infer to the surface. And what you see is that A and B are two sections where the East Reykjanes Ridge Current kind of comes together. Is the formation of those two flows that flow from the middle of the of the Iceland Basin of North Atlantic Current water. And then A is some additional flow that actually has strength at depth, as you'll see in the right image. And together, by the time they get to section C, we have about 13 sphere drips of flow. And if you look at those transports that I have in the bottom right of both images, they're the same. They show that we have about 10 to 13 sphere drips of ERRC flow, essentially all the way along those sections. However, once we get to section G in red there, which is the OSNAP line, suddenly there's a drop off of a number of 3 or 4 sphere drips. So it kind of adds into another dimension to this problem that we're having in terms of the differences in transports at section G. But upstream of it, the Argo data agrees that we have, a relatively strong flow of 10 to 13 sphere drips. So the next thing we looked at was we took cross sections or velocity cross sections of each of those sections referenced in the images now in the bottom right, and take a look at, what exactly it looks like as the water is flowing through each portion of the ERRC. And so A and B tells a nice story there of this slope intensified water in A and surface intensified North Atlantic Current water in B. And C is a nice image where you can see those two flows essentially coming together there and forming the East Reykjanes Ridge Current. And through D and E and F, you can see its kind of progression. It's a little bit more bottom intensified and pretty barotropic by the time you get to F. And finally at G, we have the current kind of diminishes at depth and it becomes more surface intensified. So in addition to the fact that the ERRC forms from that slope intensified water and the surface intensified water, we find that through all the sections A through G, all the sections A through G that is, we actually still have a maximum velocity of about 10 centimeters per second, which matches what we're finding in our OSNAP data and is notably stronger than what altimetry is finding. The big difference of section G isn't that the velocity is weaker, it's that it's not barotropic through the entire water column, and according to Argo, it's a little bit weaker at depth. And then section H, I'll talk about in a moment, but you can see that that's kind of a little bit of a weaker transport at that location. So at this point, we said, well, what's going on at section G? Where's this water going? So we decided to take a look at water flowing over the ridge. And so this is Argo data combined with altimetry for the reference velocity, since the drift velocity doesn't extend as high as it does here. And I have those section locations noted. And so this is going straight down the Reykjanes Ridge. And you'll see that there's 2 points, there's 2 pathways in particular. One right here, right at our OSNAP line. So maybe this starts to explain some of the variability of about 5.5 sphere drips. And then there's an additional pathway right over the Bight fracture zone, which is kind of the first major fracture zone, the Reykjanes Ridge south of Iceland, of about 3.5 sphere drips. And I'm looking at kind of just the maximum intensity when I'm saying those values. I have the transport within each section labeled there, but in terms of that kind of maximum velocity, that's about 3.5 sphere drips within that smaller section. And it's worth noting that even though those show kind of stronger flow at those 2 locations, it's still only 4 to 5 centimeters per second. And when you look at it in the image at the bottom there, that black line is the mean over the ridge. And the red, blue, and yellow lines are synoptic realizations from cruises. That you can see how there's a lot of variation there. And while the mean tells one story, individual synoptic realizations tell a very different story. Some of those, the red and the yellow in particular, are only a couple of days apart. And you can notice that some features have changed notably from from the few days that difference between having the research vessel go up and down the ridge. So at this point, we have an idea that we seem to have flow leaving the East Reykjanes Ridge Current in these 2 locations. It's kind of hard to see on here. Like I said, it's weak, so you can only kind of see small arrows pointing over the ridge. But it leads to this question, where does the ERRC terminate? Just look at this image, it kind of seems like right at section G or just after it, those velocity vectors really seem to decrease in size. And if you look in the next basin over, the Erminger current seems to almost form right at that location. So that's kind of our first tip, that maybe that's the primary termination location of this current. The second tip is that right here where we have where the ERRC kind of continues through section H, we actually see that there's some recirculating subpolar gyre water that's coming in there. So while the flow is kind of continuing in the same direction through the sections, it actually seems like from this Argo data that the flow is actually getting replaced by just some internal or inner basin flow, leading us to believe again that this would be our primary termination location. And if we go back to this image I showed just a moment ago, I showed A through G and how there was a maximum of 10 centimeters per second. But by the time we get to section H down here, there's a little bit, again, more evidence. And not only is the flow weaker, but what we also see is that for sections A through G, the East Reykjanes Ridge Current is this kind of ridge-hugging flow that is like a quasi-boundary current. And then by the time we get to section H, it's this off-ridge flow that's weaker. So there's a lot of evidence here suggesting that that by the time we get to section H, we no longer are looking at the East Reykjanes Ridge Current. And the final way to bring this point home is to actually look at water mass properties. So here's temperature from each of those sections. Again, the sections are in the top right. So sections A through H, and you can see the slow progression of the water cooling at every depth. But by the time we get to section H, it's notably cooler at a lot of depths, by a centimeter or so, but it's not a very far distance. It's a degree or so, but it's not a very far distance between section G and H. If we look at salinity profiles, it's the same sort of thing. It's much fresher in that final section H, once again, suggesting recirculating subpolar gyre water, most likely of Labrador Sea origin, which is known to be much fresher. And in a TS plot, putting the two together, you can really see there how it seems to be a separate water mass at this point in many ways, a much fresher water mass in particular. So this leads us to the conclusion that this pathway over the Bight fracture zone, kind of further downstream, we believe is mostly just recirculated subpolar gyre water, and that our main termination location is actually right at the OSNAP line, right at section G there. And so that's probably a lot of the reason why we have so many issues with our transport estimates at this location. Finally, the last thing that we looked at was we said, okay, this is the region where the overturning in the subpolar gyre, program. So we want to see what kind of overturning is happening here. So a way to do that is we calculated the flow weighted density, or density weighted by velocity, of transport through each of those Argo sections to kind of get a comparison of how much more dense the water becomes as we progress along the East Reykjanes Ridge Current. And so from sections A and B to section G, we found that the flow weighted density increases by 0.08 kilograms per meter cubed. So, okay, well, what does that mean? Well, when we do that same calculation for the entire North Atlantic subpolar gyre boundary current system, so from the start of the ERRC to the end of the boundary current system in the Labrador Basin, we find that this represents that the ERRC represents about a third of the total change in flow weighted density along the course of those boundary currents in the gyre. And when we look at the OSNAP value, or kind of our best OSNAP value for how much flow weighted density changes in the entire Atlantic Meridional overturning circulation, this value that we get represents about a quarter of the total flow weighted density the kind of overturning that occurs by this metric within the entire AMOC. So for this section, my conclusions are that the East Reykjanes Ridge Current forms to the south of Iceland at the convergence of surface intensified North Atlantic current water and slope intensified Icelandic slope water is the water mass that we kind of identified there. The ERRC flows westward along the southern Icelandic slope, then southwestward along the eastern flank of the Reykjanes Ridge at about 10 to 13 sphere drips. We find that its primary termination pathway over the Reykjanes Ridge is essentially right at the OSNAP line near 59 north. And according to our analysis, we believe that the ERRC is responsible for about 1/3 of the net potential density change around the rim of the subpolar gyre, or approximately a quarter of the AMOC. So now we're going to transition from the East Reykjanes Ridge Current to the North Atlantic Current here. And I have a few more moorings labeled in magenta, but just the ones that are circled there, those three in magenta are the ones we're going to look at now. Those are the three OSNAP moorings that we have, or that Miami has in the Iceland Basin. And I'm going to look at the transport of the North Atlantic Current coming into there, that kind of thick line. And I'm putting up this image that I showed a moment ago on the bottom left, because you can see from Argo, all those vectors coming right into the middle of the basin, representing the main branch of the North Atlantic Current. But you'll note that there's also a substantial branch to the east, right up against the Hatton Bank, whether you look at the vector image or the schematic. And so it's worth noting that I will not be including those values in the analysis I'm about to do right now for the next 10 minutes or so. Only looking at that kind of main branch coming in through between those tall moorings. So to do this analysis, it's similar to what I did a moment ago at the East Reykjanes Ridge Current. I'm only going to look at waters that are above the 27.8 isopycnal. Everything below it is considered North Atlantic deep water or Iceland-Scotland overflow water, and it's kind of a separate study that my advisor, Bill Johns, is working on. So I'm looking at everything above that. And once again, I'll find the difference in dynamic height. I actually, analyze the different, some of the differences between the section of M2 and M3 versus M3 and M4, those moorings there. But in general, to find the total transport, we're looking at that full section from M2 to M4. And in this case, we have to reference to altimetry. I also actually reference to a mean Argo value, which I'll show you in a moment. But, the moorings are too spread out at this point for me to reference to current meters. So when we look at those transport values, we find that the North Atlantic Current flowing into the middle of the Iceland Basin is about 13 to 14 spheredrups. And whether you're looking at Argo or altimetry in that image, they look very different, but the mean is the same. But that image tells us a lot because it says that the altimetry, the kind of reference velocity, is the main reason for our variability. The Argo value there, so just to explain for a quick moment, that transport value, I take the mean Yamaha drift value at 1,000 meters. And so that's just one number that I add to the baroclinic time series from our moorings. So what you're in a way looking at there in the Argo time series is really just the baroclinic transport reference to 1,000 meters. And you might notice that there seems to be a trend there, and there is in our 4-year time series. We find that there's an increasing trend of about 0.7 spheredrups per year in the baroclinic transport. However, when we look at the total transport represented by the altimetry time series there, we find that there really isn't much change at all. So in some way, the baroclinic transport is being offset, or the increase in the baroclinic transport is being offset by the barotropic transport. If we look at the Hobmahler plot, just like we did with the ERRC, except we'll only look at it for altimetry in this case, you can see that we have that main branch that I was showing in the schematic flowing into the Iceland Basin just to the east of mooring M3. And an additional kind of weaker branch just to the west of M3. It seems a little bit more intermittent there, but you certainly notice a clear trend of northward flowing water to the west of M3. And if I compare surface velocities from altimetry versus those inferred from Argo, they tell a pretty similar story. It's no wonder that we got basically the same transport value of about 13 to 14 spheredrups based using those two reference velocities, because they both have very similar profiles, where we have a smaller branch to the west of a little bit of an increased transport of about 4 to 5 centimeters per second, and then the main branch to the east of our M3 mooring, where we have upwards of 14 to 15 centimeters per second of mean transport. The other feature that you'll notice is that at the eastern end there's actually southward transport, and that's just due to what actually ends up being a quasi-permanent anticyclonic eddy that we have almost right over our final mooring there on the eastern end. So, in a way, maybe we're getting a little bit of an extra flow in the northward the northward flow there, just to the east of M4, but it's being offset in our transport calculation by the southward flow from the recirculating eddy. If we do an Argo cross-section like how I did with the ERRC, you can see these features pretty nicely. The more barotropic, smaller NAC branch to the west, the primary, more baroclinic North Atlantic Current branch to the east, and then at the very eastern end, that recirculating permanent eddy feature. One other thing that I noticed when I did the comparison between M2 and M3 was there was a negative correlation between the two of nearly -0.8, which they're connected by mooring M3, so it shouldn't be too shocking that there's a correlation. But the fact that it's such a strong negative correlation shows that we have what ends up being a westward propagation of anomalies from the eastern side of our section to the western side. In many cases, it seems like they're probably eddies with the opposite direction of flow, either preceding or just after it. But in some cases, it seems like it could actually be maybe a meander of the North Atlantic Current. And then the last thing to look at that really kind of tells a nice story of what's happening here is these are velocity profiles I've separated into between M2 and M3 in black and M3 and M4 in blue. And so those western values there are in black, and I referenced to altimetry and Argo by solid and dashed lines. And what they show is that that 27.8 value, where we have the separation between the North Atlantic, what I'm considering North Atlantic Current water and like recirculating Gyre water, versus North Atlantic deep water and Iceland Scotland overflow water, we have a zero velocity between M2 and M3 right at that isopycnal. And so that tells us that we have southward flowing Iceland Scotland overflow water at depth there, but then above it we have the northward flowing North Atlantic Current between those moorings. And then to the east, between M3 and M4, we actually have a bottom level of no motion here, and we kind of work our way up with northward transport all the way through, where we have some recirculating North Atlantic deep water or Iceland Scotland overflow water flowing back into the region at depth. And then above, we have kind of that baroclinic shear adding up to a surface intensified North Atlantic Current flowing in near the surface. I have that other density label there that I'll get to in a moment, but because there's a relevance to that, of course. But to finish up with the North Atlantic Current first, our analysis finds that we have 13 to 14 surge-ups of North Atlantic Current water flowing into the middle of the Iceland Basin, with a primary branch near 23.5 west and a secondary branch near 26 west. There's a positive trend in the baroclinic transport that we found, but it's mostly offset by barotropic transport. And we also realized or found that there was a clear western propagation of anomalies and a clear negative correlation between those two sections that we were looking at. It seems to be that the result of eddies in the region, some meanders in the North Atlantic Current. So going back to this image, what we have at the surface here, that is that 27 point, or near the surface, is this 27.56 isopycnal. And the reason that I have that labeled is for our third section, or the third section of this presentation, where I talk about overturning and kind of balancing a mass budget. The overturning in the Subpolar North Atlantic Program has found that our maximum density of overturning is 27.56. So at 27.56, that's where our stream function, reaches its maximum if you're adding it up as you go down in density. And so that's where we have the maximum offset of water flowing in to the subpolar gyre at the surface and flowing out below. So the upper limb and the lower limb of the AMOC. So what I'm going to do in this analysis is separate it into three sections. The red is that upper limb, and then the blue and the purple are the lower limb, but I separated that into two parts because I'm using that 27.8 value that I mentioned before that classically represents Iceland Scotland overflow water, or the origins of North Atlantic deep water, versus that middle section is more kind of cooler waters that have transformed from the North Atlantic Current or is recirculating subpolar gyre water. So in a way, I like to look at it in these three groups because they kind of each play a different role in the Atlantic Meridional overturning circulation. So I'm going to start completing this mass budget, and from the analysis I just did, I broke it up into those two density classes there. And so I have about 7.5 sphere drips flowing in the top layer, another 6 or so flowing in the middle layer, right through the middle of the Iceland Basin. From the analysis I did just a moment ago with the East Reykjanes Ridge Current, I broke that up into the flow leaving in the East Reykjanes Ridge Current there of 3.1 in the top layer and nearly 9 in the middle layer. And then also the flow over the Reykjanes Ridge of about 4 in the top layer and about 3 in the middle layer. So that's from my analysis. And then I went and collected the kind of best estimates that I could find out there from the most recent best analyses. So my advisor Bill is working on a paper right now about Iceland-Scotland overflow water, and he finds that below the East Reykjanes Ridge Current, he has about 6 sphere drips of flow departing in that region, but then also about 1 sphere drip recirculating back in, so a net of more like 5.4, 5.3. From another collaborator in the OSNAP group, I talked with him and I worked with his data, and we found that we have about 4 sphere drips in the upper layer, and then about another sphere drip in the middle layer. And this is from mean glider data. He had a glider there for about 16 months to do that analysis. In that section that's over the Rockall Plateau, that's that shallower section there. And then that same person also has recently done an analysis in the Rockall Trough where he finds about 5 sphere drips entering of the North Atlantic Current entering in the top layer, and then essentially nothing in the middle layer. Finally, the region from Iceland to Scotland there, the Iceland-Scotland Ridge, is actually the area where it has the most historical estimates, kind of the best estimates out there, because there's been so much interest in that region for so long. There's been so many studies that we have some good confidence, I think, in those numbers flowing in and out over the ridge. So when I add it all up, this tells me that I have a mass discrepancy of about 5 sphere drips. We have 26 flowing in, but then we have over 31 flowing out. So we have an issue here. Before we can even start looking at overturning, we need to try to figure out where this issue is coming from. So the first thing that I did was in the OSNAP program, we have one person that takes everybody's data, collects it all, assembles it with Argo data, altimetry, and then puts in like a very small compensation velocity for any sort of offset in the mass balance. And so I took his data and I looked at that for just this section of OSNAP to see how it compares to my best guesses. And so I know there's a lot of things here just popped up, but what the summary is that the OSNAP overall values compared to kind of my best guesses or the best realizations that I could find in each section compare really well, except for in one location, which is right here over the Rockall Plateau, where the OSNAP program is finding essentially double the transport there compared to what a recent analysis was done from one member in the OSNAP program, or one group in the OSNAP program, from some glider data in that region. So that kind of starts tipping the hand a little as to where we think there might be this discrepancy. But to analyze it further, before I get to analyzing it further, if we include all the OSNAP data and also just freeze those values from Iceland to Scotland over the Iceland-Scotland Ridge and kind of assuming those as truth, this implies that there will be about 4.5 sphere drips of flow over the Reykjanes Ridge. There was no other way I could evaluate that beyond my own analysis, except for just by doing the math and adding up what's missing. So that shows that there's 2.5 sphere drip discrepancy between my Reykjanes Ridge exit flow and what the OSNAP data implies, but we're getting closer. So so to try to solve this mystery a little bit more, what we decided to do is we said, okay, let's split right down the middle of the Iceland Basin. Let's make a section there, and let's compare the outflow to the west versus the and the inflow to the east to what we have kind of flowing through that long section. And maybe that'll kind of, again, show us that, the North Atlantic current flowing in might be our discrepancy, or maybe it'll show that we're estimating too much flow flowing out to the west. So when I do this analysis with Argo, so I'm not looking at the deepest waters deeper than 27.8, but that's okay, and I'll get to why that's okay in a moment. Argo is only in the top 2,000 meters. So to get a complete analysis, I had to exclude those waters that were more dense. But when I do that analysis, I get about 7.5 sphere drips in the upper layer and in the middle layer. And when I compare that to our original, best guesses, it turns out that this 19 sphere drips through the middle of the Iceland Basin very closely matches to what we have as our best guess exiting. So my guess of the East Reykjanes Ridge Current and what I have going over the Reykjanes Ridge and what my advisor Bill has outflowing in Iceland-Scotland overflow water matches very closely to what Argo is saying is happening in the middle of the basin. But once again, we have this discrepancy to the east where it seems like we're missing a few sphere drips. And, we're having more and more fingers at this point kind of pointing to the North Atlantic current as an underestimate of what's really happening there, or our best guess as an underestimate. So at this point, we have enough information to start kind of completing a table. So we're going to have a little bit of nerdy logic math going on here. I mean, maybe not the most intense stuff, but if it's difficult to follow, don't worry about it, because at the end I have a schematic that sums it all up, but I'll try to explain it as best as I can as I go. So from the mid-basin to the outflow values, we find that, between those two sections, there must be about 2.5 or so sphere drips of density conversion, just based on what happens from the middle to the end, from the upper layer to the middle layer, because there's no other input or output, in that area. It has to basically convert down from the upper to the middle layer. If we look at just the lowest layer now, I said a moment ago it was okay that we didn't have Argo data for here, and I'm about to tell you why. Based on Bill's analysis, he found that 6.1 sphere drips of Iceland-Scotland overflow water, that densest water, is flowing out. And flowing into this entire region is 3.6 sphere drips of this denser water. So between those two is about a 2.5 sphere drip increase in that lowest layer. Where does it come from? Well, Bill found that he was able to do an analysis with his gridded TS recorders in the OSNAP line, and was able to find that the origin waters of this additional transport was from entrainment, 1.5 of it due to actually the upper layer, as the cold, dense Iceland-Scotland overflow water flows over the sills of the Iceland-Scotland Ridge into the Iceland Basin. It entrains 1.5 sphere drips in the top layer, and then an additional sphere drip in the middle layer as it's working its way down into the basin. And so now we only have 1/2 sphere drip unaccounted for. So this is starting to balance out pretty well in the lower layer. And actually, my 3.6 value is my best estimate. Bill's analysis found that it was actually 4.1 flowing in, based on what he was able to determine. So if we use Bill's analysis, we actually perfectly balance the lower layer. And given the size of this kind of mass budget problem, for me, I say, okay, that's pretty good. Let's set that aside. And now let's just focus on the upper layer and the middle layer. So I moved those numbers that were in the upper layer and the middle layer down. And so now we're going to try to figure out what's happening here in these two layers. So if we continue to work our way backwards from the mid-basin values, in addition to the 1.5 sphere drips that's lost to the lower layer and the 1/2 sphere drip that's lost to the lower layer in the upper and middle layers, we also know that just over the Iceland-Scotland Ridge, we lose nearly 6 sphere drips in the upper layer and also another sphere drip in the middle layer. So this implies that if there is no density conversion at all, from the North Atlantic current entering through our OSNAP line to when we get to this mid-basin location, this implies that there's no density conversion at all. We must have at least 16.8 sphere drips in the upper layer that just stays there and continues through, and at most 10.8 in the middle layer that kind of stays there and continues through without any sort of density conversion. The reality is that we're pretty sure we're having water cooling and converting into this middle layer, so we would expect the upper layer to actually be more and the middle layer to be less. But if we compare this to just our original best guess, already in the upper layer, we are missing flow. You know, I said that we had to have a minimum of 16.8, and our best guess, quote unquote, has only 16.1. The middle layer, however, tells a more understandable story of water that in the middle layer that is increasing through, you know, waters becoming more dense in the upper layer through atmospheric forcing in wintertime and so on, and deep convection. So if we go and look at our best OSNAP estimate now, so look at those OSNAP numbers instead of my initial analysis, this is starting to also lead us in a better direction. The OSNAP analysis says, okay, we had about, according to that, we have about 20 spheredrups of the North Atlantic Current flowing into the Iceland Basin and further east as well. And about 3 spheredrups of that converts down into the middle layer. If we look at it from the middle layer perspective, it's about 4.5 spheredrups. It says that we're converted down, but we're getting closer. Somewhere between 3 to 4.5 spheredrups of water seems to be moving from the upper layer to the middle layer. So if I just maintain my mass conservation from my original mid-basin values and keep my ratio of upper layer to middle layer from OSNAP, so about a 3-to-1 ratio, I find that, you know, we have maybe about 21 spheredrops flowing in the upper layer, about 7 spheredrops flowing in the middle layer. And if this is a little overwhelming, in the end, with these values, what we believe is kind of our new best estimate is going to be about 20 spheredrops in the upper layer of NAC of NAC water, and somehow we're missing a few spheredrops of it, and about 6.5 spheredrops in the middle layer, and we're basically accounting for all of it. And so now, if we use these new values for what we believe is kind of the best estimate of water flowing into the basin, we can really kind of complete this overturning budget. What this means is that we have about 3.5 to 4 spheredrops moving from the upper layer to the middle layer by the time we get to the mid-basin location. And if we, okay, there we go. And if we look at those two density conversions, first from the inflow of the North Atlantic Current to the mid-basin and then mid-basin to the outflow, and we add them together, our numbers start adding up even nicer and nicer. Now we only have a discrepancy of 0.3 spheredrops. So overall, from the North Atlantic Current flowing in to where it flows out, we're contending that we have about 6 to 6.5 spheredrops of density conversion from the top layer to the middle layer. To be conservative, I'll call it 6.2. And just even out a few values in the outflow to the west, that final value down there is 11.4 now. But here's the schematic at the end. When I said that if you can't follow what's going on here, it's okay, because you know, in the end, we find that we believe that we have 20 spheredrops about coming into the eastern subpolar gyre in the form of the North Atlantic Current mostly, and then about 6.5 spheredrops flowing in as this kind of middle layer of a lot of recirculating subpolar gyre water, and then about just 4 spheredrops flowing in of that bottom Iceland Scotland overflow water. And of that, we have 1.5 spheredrops that goes through entrainment from the top layer straight to the bottom layer, a half a spheredrop from the middle layer to the bottom layer. And then the big conversion that we find is that we have about a little bit more than 6 spheredrops from the top layer to the middle layer. So again, in terms of the Atlantic Meridional overturning circulation, the value that matters here is that 27.56. And so we have a lot of water flowing from the top from the upper limb to the lower limb. And it results in the upper limb decreasing by about 40%, that middle layer essentially almost doubling, and the bottom layer also increasing by about 50%. So if I break it up into kind of the 3 sections we could look at, the OSNAP program found that the total overturning in the Atlantic Meridional overturning circulation is about 16.7 spheredrops. And so my analysis right now just found 7.8 in the eastern subpolar North Atlantic gyre here, to the east of the Reykjanes Ridge, and north of the OSNAP moorings and south of the Greenland, Scotland ridge there that the black line's going across. Historic estimates say that we have essentially 6 sphere drips that are converted from the upper limb to the lower limb in the Norwegian Sea as the warm, salty waters of the North Atlantic Current go up there and end up forming, the deepest waters in the subpolar gyre. So the greatest conversion in that sense happens there in terms of how dense those waters become. But it's about 6 sphere drips, and then it flows back into the subpolar gyre as the deepest waters. And so that only leaves about 3 sphere drips of water mass conversion from the upper limb to the lower limb that can occur in the Erminger Basin there to the west. And if we break this up by percentage, that would mean that that the Erminger Current is responsible, or sorry, the Erminger Basin is responsible for about 1/6 of the AMOC. The Norwegian seas are responsible for a little bit more than 1/3. And the eastern subpolar gyre here to the east of the Reykjanes Ridge is responsible for nearly half of the overturning that occurs in the Atlantic Meridional overturning circulation. And, and that's pretty notable considering that it wasn't too long ago that we thought that a lot of the AMOC was occurring in just the Norwegian seas and in the Labrador Sea. Since then, we've proven that nothing really happens in the Labrador Sea. And so there's this question of where's all this missing water mass transformation occurring? And so our analysis is saying that a lot of it is here in the eastern subpolar gyre. So finally, these are my conclusions, then I'm done. So for the eastern North Atlantic subpolar gyre, the total North Atlantic current flow, according to our analysis, is estimated to be about 25 to 28 sphere drips. That includes the 13 to 14 that I found, but then also everything else to the east over the Rockall Plateau and through the Rockall Trough. We find that the eastern subpolar gyre is a really important location for progressive water mass modification. As these warm, salty surface waters from the North Atlantic Current sort of just gradually transform into denser waters through deep convection in the wintertime. And this process, accounts for nearly half of the Atlantic Meridional overturning circulation, based on our analysis. And that's it. With that, I will take any questions. I got to find the questions now. I'm going to stop sharing my screen just so I can see if I can find if there's any chat stuff. Okay. All right. You're welcome, Lisa. Hi. Hey, Arthur.
How you doing, Greg? First of all, that was a very awesome seminar.
Thank you.
I like listening to a seminar where I come away from it learning a lot of things. So let me make a couple comments.
Okay.
First of all, that whole area, you're calling the current the North Atlantic Current. Some authors like to use the term North Atlantic Drift Current. So I'm just curious how you decided to use North Atlantic Current.
It was just a catch-all phrase, to be honest. I know what you're saying about the drift current. There certainly is a number of different water masses there. We have a part of the North Atlantic Current is recirculating subpolar gyre water and that sort of thing. Especially for, maybe not for the sake of this presentation, but just I feel like I'm already throwing out a lot of terms to some extent that some people might not be as familiar with. So for me, it was easier to use that catch-all, but it's a good point. It is something that in like a paper, I clarify more and I discuss the drift current a little bit more. North Atlantic drift current.
I would just want to make sure that maybe there was a new opinion that we should call the drift current, because it is an extension of the North Atlantic Current. And I thought maybe some people, decided to change the name, and I wasn't aware of it. And could you tell me a little bit about the altimeter data product you were using? Some of your results, you need to, if it was a gridded altimeter product, those areas got fairly small spatial scales that I do not think are resolved by the altimeter. So, blame some of your problems on bias errors associated with the particular gridded altimeter product.
Yeah. Great point. We have found that the altimeter product does not do a very good job of resolving flow that's particularly narrow or near topography. Right. So we've had a lot of issues with finding the altimeter product to be reliable for the Reykjanes Ridge in particular, number one. Number two, the flow over the Rockall Plateau that I talked about. For the North Atlantic Current, though, we found that it was pretty good. It's a broader flow for the most part. Argo agrees with it, and it tends to do, from what we've looked at, tends to do pretty well in areas where it's more, less topography, more flat bottom. So.
All right, thank you. I'll shut up now and let somebody else ask a question.
Okay, yes. Yeah.
Thank you for an enjoyable afternoon. I appreciate it.
Yeah, of course. Thank you so much for coming. I appreciate it.
Greg, you have a question from Lisa Beal in the chat.
Oh, okay. Let me see. I saw she said, I have a question. I didn't actually see.
Hi.
Hi, Lisa. Okay. I didn't know if it was going to be typed or, yeah, anyways.
Yeah, it was a very nice talk. I learned a lot too. And I had a question that was more of a kind of overarching impact type question that you may not have an answer to, but so, given that, you and others recently have really been finding that a lot of the North Atlantic deep water formation is actually, out to the east of the Labrador Sea, like as far as the Erminger Basin, and as you've just shown us in this region of the eastern subpolar, what did you call it? The Eastern Atlantic Subpolar Gyre.
Yeah, Eastern North Atlantic Subpolar Gyre. I know. It's like, yeah, this is going back to Arthur's thing where I'm already throwing out lots of terms,
What do you think the ramifications are, in terms of this kind of, change in geography and our understanding of where these deep waters are formed, in terms of ideas that we've had about, AMOC weakening, given, ice melt from Greenland, for example. So, because it's much farther away from those freshwater currents that come off the shelves, and flow around the rim of the western rim of the subpolar gyre there. So, have you thought about that? Is there, should we be thinking differently in terms of how, how the AMOC might respond to changes in the Greenland ice sheet, for example?
Yeah, so, certainly we should be thinking about it differently in terms of the initial analysis where we were concerned about maybe the Labrador Sea not converting as much overturning, since we now believe that there isn't very much overturning occurring there. That said, a lot of that freshening signal does kind of continue to the east. There was recently a very strong freshening signal in the last 5 years ago or so. Has progressed its way along through the upper part of the North Atlantic Current into the eastern part of the gyre. So the whole gyre itself and the kind of conversion of waters from the upper limb to the lower limb isn't necessarily in the eastern part of the gyre isn't necessarily immune, for lack of a better word, from that freshening. I would think, but your question's a good one. I haven't thought about it all the way through, but it's a good one in the sense that this intermediate water mass transformation that is happening appears to be happening a lot more in the eastern subpolar gyre now. So first order would make me think that at the very least it wouldn't be as much of an issue or implication as it would be if it was in the Labrador Sea. Since the water won't necessarily be as fresh there in the eastern subpolar gyre as opposed to the Labrador Sea. So density conversion can hopefully still continue. That said, it's such a intricate process with so many things happening that it's a good question. I haven't totally thought about it, if that will continue to hurt the overturning circulation. It makes sense that probably would some, but maybe not as alarmed as we might have been previously when we thought so much conversion was happening in the Labrador Sea. So that'd be my guess.
My second question, if I may, is so this change, is it a change over time? Was it the case that the Labrador Sea was where most of the action was happening before and now it's kind of shifted? Or is it more that we were really having our eyes on the wrong place all along?
That's a good question. Well, it brings up a whole bigger question of how we define overturning. Right now, we define overturning by like the maximum, density of the accumulated stream function, which is a good way to define it, of course. But I've been thinking more and more about this flow weighted density idea that I had when I was talking about the ERRC, and how that's a different way to define the transformation that's happening. I bring that up because in the Labrador Basin, one of the big results we found from the OSNAP program was that we were kind of underestimating the impact of the influx of fresh water in that region. So, any sort of cooling there was being essentially offset by the freshening of the water in terms of water becoming more dense. And if you actually do a flow weight analysis in that region, because I have for my ERRC paper, we found the waters were actually getting lighter, as they went through the Labrador Basin. So even though we can go ahead and analyze that there's overturning there by finding the maximum of the stream function, if you look at that full stream function, for most of the depth, it is water getting lighter, not water getting more dense.
Right.
So I say that because it makes me think that, depending on how we define overturning, it makes me think that the Labrador Sea was an area that we were maybe kind of overestimating what was happening there to begin with. I know there was a lot of analysis there originally, but when you kind of look at it through the full picture, I think it's easier to take a simple spatial section and kind of do your own analysis without looking at the whole. And so I think that once we look at the whole, maybe it was a case where we were accounting for too much the whole time in the Labrador Sea. That being said, there certainly could be.
Because I guess, although there was, because what was really exciting about the Labrador Sea was those giant convection, 2,000 meter deep convection that were found. But in fact, you're saying that, but then that deep water has to mix with this very fresh, current around the edge, right? It has to mix with that to get out and go south. And so in doing that, it's actually getting lighter. Is that kind of the gist of it, or?
Yeah, I mean, exactly. I mean, so it's mixing, so it's doing that deep convection, but in the long run, that water that ends up getting exported is still, according to flow weighted density, still like a little bit lighter, just because of the influx of fresh water. And so that Labrador Sea water certainly is part of what's being exported. A lot of it is also just recirculating back through the gyre. So I think we look at that and we kind of attribute that there's deep water formation there, and and there is to some extent, but it's not necessarily being exported. A lot of it's just staying in the gyre, recirculating and mixing in with the boundary currents that then kind of works its way out of the gyre eventually.
Right.
Can I do a quick follow-up? So do you think the Labrador contribution to this, is it order 0% or order 10%?
Depends on how you define it. I am working on another paper where I'm basically going to say it's order negative 0% to some extent.
Okay, no,
yeah. Well,
right now, not hearing your talk, I would say 10%. Right?
Yeah, well, no, but I'm working on a paper doing that flow weighted density concept, and so I shouldn't say it's negative or anything like that. I mean, it's what I was saying to Lisa a moment ago, where its contribution is, it certainly is having some deep water formation through that, really deep convection. So much of that's just getting recirculated back in the gyre. What's actually kind of flowing into that basin through the West Greenland Current and flowing out through the Labrador Current, from start to end, overall is lighter. Not by a lot, but by a little bit. So that's not overturning. That's
So I'm kind of taking up all the questions, but going back to the previous question about is it a change over time? So do you think there's some potential there? If it's just getting a little bit light, there's some potential that if there's fresher water in those boundary currents now than there was, 20 years ago, whenever the Canadians, started doing their repeat.
Right. Yeah. So I should have clarified, it's probably a bit of both, and that's a great point. Just the, more recent ice melt, certainly, you would guess is going to be a greater contributor based on our OSNAP results. So yeah, I'd say it's a balance of the two things. I'd say it's, to some extent, it's easy to look at a stream function and kind of pick its maximum for your own individual section and say that, I have, this many surge of transport that are overturning. But also, I agree with what you're saying. It does seem as though, no matter how we compare our OSNAP values to what's been found in the past, we are still less. So there seems to most likely be some sort of transformation that's happened there, and probably from the freshening of the waters from the, more intense ice melt from Greenland.
Thank you again. It was very nice work.
Yeah, of course. Thank you. Thank you for coming. All right.
Okay, if there are no further questions or comments, Mary Beth, do you want to say something?
Nope. Great job, Greg. That was a really great seminar.
Yeah, great job. So we can thank him again for
the
presentation. And I thank everybody in the audience for joining our Zoom session, which was recorded. So if someone wants to watch it again, or someone wasn't here and wants to watch it later, we will have the Zoom link. I will send it to Greg so he can send it to people who want to watch it. And next Wednesday, we will have the big Best Student Seminar Award ceremony for academic year 2019-2020, which will be fully online, but there will be real chocolate bunnies and real money and real certificates, and everything will be real except that it's online. So I hope everybody will come, and especially the students should all come to see if they get an award. And between then and now, we still have 3 more students speaking this Friday morning, so I hope to see you there as well. Those will be the last ones who compete for the Best Student Seminar Awards 2019-20, and then after that we will begin with the 2020-21 seminars. Okay, thank you, goodbye, see you again on Friday.
Thank you, Roland.